Besides the Cartesian or rectangular form, complex numbers can also be written in polar form. Learn how this is done here in Mathematics of Engineering. A complex number in polar form is configured as z is equal to r cis theta. Cis is short for cosine plus I sine. Thus, z in polar form is expanded as r times cosine of theta plus I times sine of theta. In this standard polar form, we are only to look for the modulus r and the argument theta. How do we determine the modulus and argument? Let's transform 1 plus 2y. Graphing the complex number in Cartesian form, we place the real number into the x-axis and the imaginary number takes the y-axis. With the real number 1, draw a vertical line from the x-axis. And 2y can also be drawn as a horizontal line from y as equal to 2. The intersection is marked and the complex number can be drawn as a vector. The length of the vector is tagged as the radius, as the complex number is considered as a rotation on a 2D plane. As it is the length of the vector, this is the magnitude of the complex number, which is denoted as z in modulus, which can also be interpreted as the absolute value of the complex number. Because r is length or distance, r should always be positive as there is no negative distance or length. With the triangle form, using Pythagorean theorem, r is solved as x squared plus y squared. For the example, r is then the root of 1 squared plus 2 squared, which is equal to the root of 5. The second needed parameter is theta, which is the angle of rotation referred from 0 degrees. Just like the flow of the quadrants, theta is measured in a counterclockwise rotation. With the known x and y components, using trigonometric functions, specifically tangent of theta gives y over x. The angle theta is then solved as the inverse tangent of y over x. From the example, theta is then the inverse tangent of 2 over 1, computed as 1.107 in radians. Knowing the two parameters, r as root of 5 and theta as 1.107 radians, z can then be identified by plugging them into the standard form, z as r cosine of theta plus I sine of theta. Thus, the polar form of 1 plus 2y is root of 5 times cosine of 1.107 plus I times sine of 1.107. Another example to convert is z as 4i. This can be considered as 0 plus 4i, which means no x-coordinate and 4 from the y-axis. The vector is then drawn as a vertical line pointing upwards to positive 4. The length of the vector is also 4. This is r, and from the graph, theta is shown as 90 degrees, or pi over 2 in radians. So from the standard polar form, we can write z as 4 cosine of pi over 2 plus I sine of pi over 2. This can also be shortened as 4 cis pi over 2. What if z is negative 4i? There is still no real coordinate, and the imaginary number points to negative 4. That is, a vertical vector pointing downwards. r is then taken as 4, and theta starts from 0 degrees all the way to 270 degrees. This is the same as 3/2 of pi. With r and theta already known, place them in the polar form as 4 cosine of 3/2 pi plus I sine of 3/2 pi, which is written similarly as 4 cis 3 pi over 2. The next example has z as plainly 3. This is purely a real number, or the imaginary part is 0. We draw this as a horizontal line pointing to the right. This is already the vector with r equal to 3 and theta as 0 degrees. Z in polar form is then 3 cosine of 0 plus I sine of 0, shortened as 3 cis 0. If z is still a real number but negative, the graph can be drawn as a horizontal vector pointing to the left at -3. R is taken as 3 as it measures the distance, regardless on which quadrant it is drawn. Theta is taken as 180 degrees, which is the same as pi in radians. So z in polar form is written as 3 cosine of pi plus I sine of pi, or 3 cis pi. With z as -4 plus 4i, we can draw the coordinates at x of -4 and y at +4. So the vector is on the second quadrant. Its length is then computed as the root of the coordinates -4 squared plus 4 squared. That would be the root of 16 plus 16, which is 32. R is then 4 root of 2. Theta, on the other hand, is the inverse tangent of y over x, that is, the inverse tangent of 4 over -4, which gives theta as -pi over 4. As it is negative, this theta is drawn from 0 degrees just the same, but it is a quarter of pi clockwise, which shows a vector pointing opposite the original vector. In order to coincide with the vector we're solving, we add 180 degrees or pi. Thus, theta becomes 3/4 of pi. Knowing r and theta, we write the polar form of z as 4 root of 2 times cosine of 3/4 of pi plus I sine of 3 pi over 4, or that is 4 root of 2 cis 3 pi over 4. Take a look at this next example with z as -6 minus 3i. By drawing the x-coordinate as -6 and y-coordinate as -3, we get a vector in the third quadrant. The magnitude is then solved as the root of -6 squared plus -3 squared simplified as the root of 36 plus 9, making the root of 45. This is the same as 3 root of 5. Theta is the inverse tangent of y over x, that is the inverse tangent of -3 over -6, giving theta as 0.464. Take note that this is in radians, where pi is 3.1416. Thus, theta is located in the first quadrant, oppositely located from the vector of our concern. Adjust theta by adding 180 degrees or pi, making theta as 3.605. Therefore, z in polar form is 3 root of 5 times cosine of 3.605 plus I sine of 3.605, simply written as 3 root of 5 cis 3.605.